and welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, in the last 2 weeks, we started learning about the pile foundation. So, we learned about the calculation of load carrying capacity of a pile in compression uh, using two methods. So the first one is static pile load formula, and the next one is using the load settlement data obtained from pile load test, vertical pile load test. Now, in this week, uh, we we have learned about two more ways by which we by which also we can determine the load carrying capacity of single pile. Now, uh, these two methods are pile driving using pile driving formula, and the fourth one is basically based on some some correlation with penetration test data. Okay, so therefore, from this specific course, we will learn about the estimation or calculation of load carrying capacity of pile in compression using four uh, different methodologies, or by four different ways, which are using static pile load formula, then using the data obtained from pile load test, then pile driving formula, and lastly correlation with penetration test data. Now this is for single pile. So we can also determine the group action of piles when the piles are basically arranged in group. Then we can determine the load carrying capacity of pile group in plane and settlement of a pile group. Okay, so these additional topics we have learned from this week, and lastly we have learned about the estimation of negative skin friction in single piles and group of piles. Okay, so through this session we'll see how to basically utilize these concepts for or to solve a couple of numerical problems. Okay, so we'll start this session with this problem. This problem basically we took in the last session as a homework problem. So we'll basically first solve this problem, and we'll subsequently move to a few new problems which cover the aspects which we have mentioned just now. Okay, so the first problem deals with a 16-meter long concrete pile which is driven into a layered soil stratum in such a way that the pile head is 1 meter above the ground level. The subsoil profile and the respective properties are given in the table below. The water table is at a great depth from the ground level. If the diameter of the pile is 0.3 meter, determine the safe load carrying capacity of the pile. Consider the angle of wall friction is 0.75 times the angle of internal friction of the soil. Now, these are the subsoil profile. This is the subsoil profile. So layer 1, which is basically extending from 0 to -6 meter, and the soil type is soft clay, which is having a unit weight of 15 kilonewton per meter cube, and unconfined composite strength 40 kilonewton per meter square, and adhesion factor 1. For the second layer, it's having a thickness of -10 to -6, so therefore 4 meter. So it's a dense sand in nature, and it's having a unit weight of 17 kilonewton per meter cube, angle of internal friction 35 degree, and coefficient of earth pressure 2. And for the third layer, it's extending from -10 meter to -15 meter. It's steep clay, having a unit weight of 19 kilonewton per meter cube, and unconfined composite strength 120 kPa, adhesion factor 0.2. So based on the soil profile, we will try to determine the safe load carrying capacity of the given pile, which is having a length of 16 meter and diameter 0.3 meter. Okay, and please keep in mind that this whole length is not embedded into the ground. So 1 meter, the pile head is basically 1 meter above the ground level. So the penetration depth is only 16 minus 1, that is 15 meter. Okay, so for the calculation of load carrying capacity of the pile, we'll have to consider this length, that this is not the whole length of the pile, this is only 16 minus 1, that is 15 meter of the pile length. Okay, so this is the pictorial view of the pile. So as you can see from this figure, that this pile is basically embedded through 3 different soil layers. So the top layer is a soft clay having these properties, basically mentioned in this slide. Then the second layer is dense sand, and lastly the third layer is slip clay. Okay, and pile head is at an elevation of 1 meter with respect to the ground surface. Now, as you know that the ultimate capacity of a pile is derived from point bearing resistance. So Q it is the summation of point bearing resistance QPU plus UF, that is the ultimate skin friction resistance. Okay, so this point bearing resistance, this can be determined from unit point bearing resistance multiplied by the cross sectional area at the pile tip or pile base. Similarly, the ultimate skin friction resistance can be determined by multiplying unit skin friction resistance. Okay, so multiplied by the surface area of the footing. Now this AB and AS. Okay, so first of all we will concentrate on this first term, that is QPU times AB. So QPU, since the pile tip is rested on a steep clay deposit. Okay, so therefore this QPU, it will be CU NC, simply CU times NC. Okay, now this CU, this is, we can determine from the unconfined compressive strength of steep clay. So CU, it would be QU by 2, that means 60 kPa. So therefore this is 60 kPa, and NC, as we know, it's 9 for a deep foundation as per Skimton's theory. So this value would be 540. Therefore, your AB, okay, so final QPU, ultimate point bearing resistance, would be 540 multiplied by AB. AB is nothing but pi by 4 d square, and the value of D, so this is D, this is the diameter of the pile, so it is given as 0.3 meter for the present problem. 0.3 meter, so it's multiplied by 0.3 square. So 550 multiplied by pi by 4 into 0.3 square, so it will give you the ultimate point bearing resistance as 38.2. Okay, So this is for the ultimate point bearing resistance. Now coming to the skin friction part, so QF, so it will be having three components because the pile length is basically driven, or the pile is driven through three different layers: soft clay, dense and stiff clay. So the contribution to the skin friction resistance from these three layers will be different. So you have to calculate the contribution from each of these layers individually, then you have to add these three components to get the final skin friction resistance. Okay, so therefore this QF, it will be having three components like QF1, QF2, QF3. Okay, going one step ahead, so it will be FS1, AS1, FS2, AH2 plus FS3, AS3. Okay, so FS1, FS2, FS3 are the unit skin friction resistance for each of these individual layer respectively, and AS1, AS2, AS3 are the corresponding surface area of the pile. Now, since the pile is basically driven through three types of soil: soft clay, dense sand and stiff clay. So for clay, Fs, you can calculate from using this formula alpha Cu. Okay, and for sand, this Fs, you have to calculate using this formula A times sigma B average prime. Now for first and third layer, we'll use the first formula, that is alpha times Cu, and for the second layer we'll use this expression K times sigma AB average and delta. Okay, so QF1, that is the ultimate skin friction resistance contributed by soft clay, so it will be alpha times Cu. Now what is the value of alpha for soft clay? So it's basically 1. Okay, so it's given to this problem. And what is the value of Cu? The value of Cu, it will be 20 kPa. Okay, following the same logic as we applied for stiff clay. So as we know that undrained coefficient is nothing but half times the unconfined compressive strength of the soil. So unconfined compressive strength of the soft clay is given as 40 kPa. Therefore, undrained coefficient of the soft clay would be 40 by 2, that means 20 kPa. Okay, so QF1, it will be 1 times 20. Now this value you have to multiply with the corresponding surface area of the pile. Now what is the corresponding surface area of the pile in layer 1? So this is layer 1. So this is layer 1, this is layer 2, and this is layer. So the surface area of the pile in layer 1, it will be pi d, that is the perimeter of the pile, multiplied by the length. Now what is the length in layer 1? It will be 6 minus 0, that is 6 meter. Okay, so pi d, diameter of the pile, so it will give you the perimeter multiplied by 6. Okay, so this is the length of the pile in layer 1. Now if you calculate this value, so I hope this value would be 20 into 5 into 0.3 into 6. 1 13.1. So this is for layer 1. Now for layer 2, since this is a dense sand, so you have to use this expression, the second expression, K times sigma AB average times delta. Now what is the earth pressure coefficient given for this layer? So this is 2. So it will be 2 multiplied by sigma average, the effective overburden pressure, average effective overburden pressure for this layer. Now in the problem statement, it's given like that the water table is at a grade depth from the ground level. So whatever stress, total stress you will be getting at the top and bottom of this layer, so that will be the effective stress since forward pressure is 0, and average of those two values will give you the average effective overburden pressure for this layer 2. Now what will be the effective stress at the top and bottom of this layer? So first we have to calculate that, otherwise we will not be able to calculate QF2. So here I am calculating. So for layer 2, first of all we are calculating at the top. So this is sigma V prime or sigma prime. So for top it will be simply gamma of pass layer multiplied by thickness of layer 1, that is 15 multiplied by 6. 15 multiplied by 15 multiplied by 6. Okay, so and coming to bottom, so it will be I hope 15 multiplied by 6 plus 17 multiplied by 4. Okay, so 15 multiplied by 6 plus 17 multiplied by 4. Why 4? Because this is the thickness of the second layer, that is 10 minus 6, that will give you a thickness of 4 meter for layer 2. So 15 multiplied by 6, okay, so I hope no, it's fine. So plus 17 multiplied by 4, that is 158, and here this is 6 multiplied by 15. Okay, so please check the values once more. So here this is 17 kN per meter cube, this is 15 kN per meter cube, and we are determining the sigma average for this layer 2. So it will have a value of at the top 15 multiplied by 6, that is 90, and at the bottom 15 multiplied by 6 plus 17 multiplied by 4, 158. Okay, so now so therefore this average would be 90 plus 150 by 2. Okay. Okay, just give me a few minutes. I'm facing one problem. So, okay, we have got the average effective overburden pressure for layer 2 as 90 plus 158 by 2. And I think it's clear how we have got this 90 and 158. So 90, that is at the top of this layer, which we have got by after multiplying 15 with the thickness of first layer, and this 158 we have got, this is plus the overburden due to layer 2. Okay, so that is 17 multiplied by 4. Now, okay, obviously this is in kPa. Now multiplied by tan delta. Now delta, this is given as 0.75 times 5. Now what is the value of 5 for layer 2? It's 35 degree. So that means 0.75 multiplied by 35. Okay, so this is the unit skin friction resistance for layer 2. Now this value we have to multiply with the corresponding surface area. So corresponding surface area would become pi times 0.3 times the length. So length of the pile in layer 2 is 4 meter. That is 10 minus 6, that is 4 meter. So this will be the ultimate skin friction resistance contributed by layer 2. Now please calculate and let me know what would become the value. So 90 plus 158 multiplied by tan of 0.75 into 35 to pi into 0.3 into 4. So 460, I am getting something 461.1 Newton, obviously for layer. And finally for layer 3, it will be again alpha times Cu, because this is steep clay. Okay, and what is the value for alpha? Alpha value is 0.4, and what is the value for Cu? It's 60 kPa. 0.4 times 60 multiplied by pi into 0.3. Now what is the length in layer 3? It's 15 minus 10, that is 5 meter. 0.4 times 60 into pi into 0.3 into 5, that is 113.1 Okay. Now we'll add all these three components to get the ultimate skin friction resistance. So 113.1 plus 461.1, again 100. Okay, so now after adding these three components, we'll have QF value as 687 millimeter. Therefore, ultimate load carrying capacity of the pile, so this will be 38.2 plus 687. That means 725.5. So please correct me if I am wrong in the calculation part. So therefore, safe load carrying capacity will be QU by factor of safety 725 divided by 2.5. That means 220.2. So to calculate the safe load carrying capacity of the given pile, first you have to calculate the point bearing ultimate resistance of the pile, and you have to divide that ultimate load carrying capacity of the pile with an recommended factor of safety of 2.5. However, to get the ultimate load carrying capacity, you have to calculate the ultimate point bearing resistance and ultimate skin friction resistance separately. Now, ultimate skin friction resistance you can easily get from this equation QPU times AB. However, this QA, it will be contributed by all these three layers, that is layer 1, layer 2 and layer 3. So for layer 1 and layer 3, you have to use this equation alpha times U for the unit skin friction resistance, whereas for layer 2 you have to use this equation for unit skin friction resistance, since layer 1 and layer 3 are clay and layer 2 is sand. Okay, so this way you can calculate the safe load carrying capacity of the given pile. Now we'll take this problem. This problem is related to determination of safe pile load using modified Illes formula. So this is an example of the calculation of pile load capacity, safe load carrying capacity of pile using dynamic pile load formula. Okay, so far we have calculated the load carrying capacity of pile using static load formula and the data obtained from the pile load test. So through this example, we'll see how to utilize the dynamic formula to calculate the load carrying capacity of a given pile. So the problem statement is like that: a single acting steam hammer of weight 25 kilonewton and a height of fall 2 meter was used to drive a pile of 300 mm diameter. Determine the safe pile load using modified Illes formula using the following data: length of the pile 13 meter, hammer efficiency 0.8, unit weight of concrete 24 kilonewton per meter cube, the value of E as 0.5, factor of safety 2.5, and the average penetration of the pile in the last 20 blows 3 mm, and consider that during the pile driving a cushion of 2.5 centimeter was only used. So therefore, to solve this kind of problem, first we have to see what is the formula given by this modified Illes, or what is the modified Illes formula to determine the safe pile load. So this is the modified Illes formula. Okay, So as per this formula, the ultimate load you can determine by using this equation, which is nothing but W times H times eta H times eta divided by S plus C by 2. Now this C will be having three components, C1, C2 and C3. So we'll see subsequently what are the physical significances of each of these parameters involved in this equation. So first of all, QU, this is the ultimate driving resistance in tons. Okay, so please keep in mind. So this empirical equation will give you the ultimate driving resistance in tons. Therefore, to calculate the safe load, you have to divide this ultimate resistance by a factor of safety as given to this problem as 2.5. Okay. Now coming to W, this is the weight of hammer in tons. So what is the weight of hammer in tons for the given problem? So the weight of hammer is given as 25 kilonewton. Therefore in ton it will be 2.5. Okay. Then H, this is the effective fall of hammer in centimeter. Now what is the effective fall of hammer? So the effective fall of hammer is given as 2 meter in this problem. So converting it to centimeter, it will be 200 centimeter. Okay. Now what is the hammer efficiency? Eta H is the hammer efficiency. So this is given as 0.8 directly to this problem. Okay. Then S, this is the final set or penetration per blow in centimeter. So in this problem, the average penetration of the pile in the last 20 blows is given as 3 millimeter. So in centimeter it will be 0.3 centimeter per blow. Okay. Now two parameters are yet to define. So the first one is eta and the second one is C. So eta, this is the efficiency of blow that represents the ratio of energy after impact to striking energy of ram. Okay, so that we will see how to calculate this eta. And coming to the second parameter C, that is the total elastic compression, and it's a summation of three components C1, C2, C3, that we will also see in the next slides how to determine this value. Now one more thing, that in this problem eta H, that is the hammer efficiency, is directly given to this problem. If this is not the case, we can also determine this value using this table, that is the hammer type. This table is basically giving you the information about the hammer type and the corresponding efficiency. So this is a since this is a single acting steam hammer, so its efficiency will vary in between 0.75 to 0.85. So you can basically assume an average value of this range. Okay, so 0.75 plus 0.85 divided by 2, so that will give you 0.8. Okay, however in this problem this value is directly given to you, so therefore we will use this value only. Okay, now coming to eta, this eta can be calculated by using this equation. There are two equations. So the first equation is applicable when the weight of hammer is greater than P times E. So we will see what is P times E, and you have to use the second equation when the weight of hammer is less than P times E. Now P is weight of pile plus anvil plus helmet plus follower if any in tons, and E is the coefficient of restitution of material under impact and ranges from 0 to 1. So this E value is directly given to you, and this is 0.5 for the given problem. Okay, now what is the value of P? W already we have calculated, so the value of W is basically 2.5 ton. Okay, now what is the value of P? So to calculate the value of P, since this is the weight of pile, so this is the weight of pile, so you can calculate this weight by multiplying the unit weight of concrete with the volume of the pile. Now what will be the volume of the pile? This will be pi by 4 d square cross sectional area multiplied by the length. Now what is the unit weight of the concrete given to this problem? So unit weight of the concrete is given as 24 per kilonewton per meter cube. So this is 24. And what is the pile cross section? So pile cross section is basically circular, having a diameter of 300 mm. Therefore this will be 0.3 square. And what is the pile length? So pile length is 30 meter. Okay, so multiplied by 30. So it will give you the weight of the pile. So pi into 0.3 square into 13 divided by 4 into 24. So this will give you the pile weight as 22 kilometer. So that means 2.2 ton. Okay. Now we have to compare the weight of hammer and the product of weight of pile and the coefficient of restitution. So now what is this P times C value? So here I am calculating this weight of pile multiplied by E. So this value would be 2.2 multiplied by 0.5. That means 1.1 ton. Now if you compare this W and P, so obviously W will be greater than P. Okay, so this value is less than W. 2. So weight of hammer is 2.5 ton, whereas this product PE is 1.1 ton. So obviously weight of hammer is greater than this product. So you have to use this equation to calculate the efficiency of blow, eta. So what will be the value then using this equation? So it will be 2.5 plus 2.2 into 0.5 square divided by 2.5. So if you calculate, then this value would become approximately 0. So we have got the value for eta. So the last value which we have to still figure out, that is the value of C. And to calculate this C value, you have to calculate this components C1, C2 and C3 individually. Then you have to add these values to get the C value. Okay. Now this C1, C2, C3 you can calculate by using this table. So C1, this is the temporary elastic compression of dolly and packing, and it will be having a value of 1.77 times Q by A, where the driving is with 2.5 centimeter thick cushion only on head of the pile. And I think this is applicable for this problem. Why? Because it's mentioned in the problem directly that consider that during the pile driving a cushion of 2.5 centimeter was only used. Okay. So if this is not the case, if the case is when the driving is with short dolly up to 60 centimeter long, helmet and 7.5 centimeter thick cushion, then you have to use this equation 9.05 times Q by A to calculate C1. Now what is QU? QU, this is the ultimate resistance of the pile, and what is A? This is the cross-sectional area of the pile in centimeter square. Okay, so this is for C1. So we'll use this equation 1.77 times Q by A to calculate C1, since the driving is with 2.5 centimeter thick cushion only on the head of pile. Okay, now coming to C2, it's a temporary elastic compression of pile, and you can calculate this C2 value from this equation 0.675 times QUL by A. So QU, again the ultimate resistance of the pile, L length of the pile in meter, and A, this is area of pile in centimeter square. Please be very careful about the unit system, since we are using an empirical equation to calculate the pile resistance. So whatever unit system is used or was used in deriving the formula, you have to only use, or you have to confine yourself only that unit system, that unit for each of the individual parameter. As you can see that L is used in meter, that is SI system, whereas A, this is in CGS, centimeter square. Okay. Now coming to the final component C3, this is the temporary compression of soil, and you can calculate this temporary compression from this equation, 3.55 times Q by A, Q ultimate resistance of the pile, and A, this is the pile area in centimeter square. Okay, so now we'll calculate these components one by one. So this C, so this is 3 components, C1 plus C2 plus C3. For C1, this is 1.77 QU by A, 1.77 QU by A. For C2, this is 0.675 QU L by A. And for C3, this is 3.55 QU by A. Okay. So we'll take this QU by A in common. So 1.77 plus 0.675 L plus 3.55 by L. Now what is the value of L? So L is basically 13 meter. And what is the value of A? This is pi by 4 into 30 square. Since you have to incorporate the value of A in centimeter square. Okay. So pi by 4 into 30 square, this will give you the area as 706.86 centimeters. So 1.77 plus 0.675 into 13 plus 3.55 Q by 706.86. So this value will be approximately 2 into 10 to the power minus 2. Okay. Now we know all the parameters which are involved in the modified Healy equation to calculate the safe pile load. First of all, ultimate pile load. Okay. Now what is the equation? So QU this is W H beta H beta divided by S plus C1 C2 C3. Okay, or we can write only C by 2. Now these parameters are, so W, this is the weight of hammer in ton, 3.5. This is the height of fall of the hammer in centimeter, 300 centimeter. Beta H, this is the hammer efficiency given as 0.8. Beta efficiency of blow, we have calculated it as 0.65. Is this is the final set per centimeter, final set per blow. This is given as 0.3 centimeter per blow. And C, we have calculated it as 2 into 10 to the power minus 2. Okay. Now we'll substitute these values in this equation. So QU, this will be 2.5 multiplied by 200 multiplied by 0.2 multiplied by 0.65 divided by 0.3 plus 10 to the power minus 2. Okay, so 2 by 2, so it will be only 10 to the power minus 2 QU. Now please see that this will become a quadratic equation in QU. How? So this will be QU square plus 30 QU minus 26 equals to 0. So if you simplify this equation, so it will become a quadratic equation in QU. Now you have to solve this equation. So after solving, you will end up with the QU value as 147. Okay, again this value is an approximate value. Okay, now you have got the ultimate pile resistance. So the safe pile load, it will be simply ultimate by the given factor of safety, which is 2.5. It will be 58.8 ton. That means 588. Okay, so by using this formula, you will get the QU value in ton. Please keep in mind. So after getting the QU value, you have to divide this value by the recommended factor of safety to get the safe pile resistance or the safe load carrying capacity of the pile. Okay, so in this way we can implement the dynamic pile load formula, obviously modified LS formula, to calculate the safe pile load. So there is one more formula to calculate the safe pile load. So under this category, dynamic pile load formula, that is the engineering means formula. Okay, so though we will not basically due to time bound, we cannot basically solve example problems using that formula. So we have already seen how to calculate the modified safe pile load using modified LS formula, and in a similar manner you can also calculate the safe pile load using engineering means formula. Okay, so now we'll calculate the ultimate load carrying capacity of the pile based on some correlation with the SPT n value. Okay, so the uncorrected n values obtained from a standard penetration test done in a soil stratum of dry sand are given in the table below. A pile of 0.4 meter diameter and 10 meter length is driven into the soil such that the pile head is in line with the ground surface. Determine the ultimate load carrying capacity of the pile. So we have seen the application of static pile load formula, dynamic pile load formula, and the pile load test data to calculate the load carrying capacity of a given pile in computation. Now with this problem or through this problem, we will additionally see the calculation of ultimate load carrying capacity of a pile based on correlation with the SPT n value. So this is the SPT n value which are basically given for an elevation from -1 meter to -12 meter, and it's mentioned in the problem that this pile head is in line with the ground surface. Okay, so this you can also see from this figure that the pile head basically is matching or is in line with the ground surface. Now how to calculate this ultimate load carrying capacity of the given pile using the SPT test data? So to calculate the ultimate load carrying capacity using the SPT test data, you have to go for some empirical correlation. So this is the correlation. So as you know that this ultimate resistance is basically contributed by two components. So QU, this is the summation of QPU and QA. That is the ultimate point bearing resistance and the ultimate skin friction resistance. So ultimate point bearing resistance you can get after multiplying the unit point bearing resistance with the cross sectional area of the pile at the pile base, and this ultimate skin friction resistance you can get after multiplying the unit skin friction resistance with the corresponding surface area of the pile. Now this QPU, AB and AS, it's very easy to calculate because the pile geometry is directly given to you. So AB, so this will be simply pi by 4 d square, and this AS, this will be pi dl. Okay. Now for the given problem, you can calculate this AB. So it will be pi by 4 times 0.4 square. So 0.4, this is the diameter of the pile. So it will be 0.126 meters square. And for surface area, it will be pi times 0.4. And what is the length of the pile? So length of the pile is 10 meters. So therefore, it will be 12.57. Okay. Okay, so AB and AS we can directly calculate, and already we have done that part. So now the rest or the remaining part is to calculate the QPU and FS. So this QPU and FS you can calculate by using this equation. So QPU, it will be 40 times N L by D in kilonewton per meter square, where N is the standard penetration resistance observed in field without overburden correction. Okay, so please be very careful that you need not to implement any overburden correction on the observed SPT data to calculate the QPU. So it will be the uncorrected value only. Okay, and L, this is the length of the pile, D, this is the diameter of the pile, and obviously after using this equation, the value should be limited to a value or upper bound of 400 times N. So this is for the QPU component. Okay, so this is for the unit point bearing resistance. Now what is about the unit skin friction resistance? So unit skin friction resistance, so depending on the type of piles, you have to use the equation. So first of all, for displacement piles, which is applicable for a driven pile, so this will be 2 times N average, and again it will be having a limiting value of 100 kN per meter square. And for H piles, this is only N average and limited to 50 kN per meter square, where N average is the average field value of N along pile length. Okay, so we'll calculate one by one. So first of all, we'll calculate the QPU. So QPU, it will be 40 N times L by D. Now 40 into this L by D. So L for the given pile is 10 meter and diameter is 0.4. Okay. So we'll first check the limiting condition. So this will be 10 by 0.4, that means 25 multiplied by 40, that means 1000 times N. And this is obviously greater than 400. So you have to use the limiting value of the unit point resistance, point bearing resistance, as 400. Okay, so the QPU, this will be. Now what is the value of N at the pile tip? So the value of N at the pile tip, so what is the length of the pile? So length of the pile is 10 meter. So at an elevation of -10, the N value is 56. So therefore you have to use this 56 for calculating the unit point bearing resistance. So 400 multiplied by 56, so this will give you the unit point bearing resistance as 22400 kilonewton per. Okay, so this is the unit point bearing resistance. Now coming to the skin friction resistance. So unit skin friction resistance Fs, since the pile is basically driven. Okay, so it's basically driven. A pile of 0.4 meter diameter and 10 meter length is driven. So therefore you have to use the equation which is applicable for displacement piles. That means 2 times n average. And again you have to check whether the limiting value is exceeding or not. Okay, so if it is exceeding, then you have to use the limiting value only. So 2 times n average. So this is for driven piles. Now what is the n average? So n average, this is the average SPT n value, uncorrected SPT n value along the length of the pile. So you have to basically take an average of all these n values up to an elevation of minus 10 meter. So starting from -1 to -10, you have to take an average of all these given n values. So n average, it will be 1 by 10, since there are 10 data points or 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be 44 plus 46 plus 48 plus 50 plus 52 plus 52 plus 55 plus 55 plus 56 plus 56. Okay, so if you take an average of all these 10 values, I hope the average value would become 51. Let me check it once. So yeah, it's 51.4. So you can take this value as 51. So this is the average in average. Okay. Okay. Now coming to this Fs part, so it will be 2 times 51, 102 kilonewton per meter square. Now what is the limiting value? So the limiting value is 100 kilonewton per meter square. So obviously this value is greater than. So therefore you have to consider the Fs, or you have to limit the Fs 100 kilonewton per meter square. Okay. Now you know Q, Pu and Fs, so you can multiply this AB and AS with Q, Pu and Fs respectively, and you have to add these two components to get the ultimate load carrying capacity of the pipe. So ultimate load carrying capacity Q, so this will be Q, Pu, AB plus Fs. So Q, Pu, AB, this is 0.126 plus 100 multiplied by, what is the value of AS? 12.57. Okay, so this is 4079.4. So this is an example through which we have seen how to basically utilize the SPT test data to calculate the ultimate load carrying capacity of a given pipe. Okay. So now we'll take another problem, and this problem is taken from GATE examination 2023. So in this problem, a group of 9 friction piles are arranged in a square grid maintaining equal spacing in all directions. Each pile is of diameter 300 mm and length 7 meter. Assume the soil is cohesionless with effective friction angle 32 degree. What is the center to center spacing of the piles for the group efficiency of 60%? So as you can see from this figure, so this is the plan view of the group of 9 friction piles, and these friction piles are basically arranged in a manner that it's maintaining equal spacing in all the directions. Okay, so this spacing, suppose this is S and this spacing S are equal. Okay, though the figure basically doesn't confront to this statement because this is not in scale. This figure is not in scale. Okay. Now, what is the diameter of the pile? So the diameter of the pile is, and length of the pile is 7 meter. Now, what you have to do? You have to basically determine the center to center spacing of the piles. That means this S value. For what? For the group efficiency of 60%. So therefore, you have to calculate the group efficiency first. Now, what is meant by group efficiency? What is meant by group efficiency? So group efficiency, this is the ratio of the capacity of the pile group divided by n times capacity of individual pile UI. Okay, so this will give you the group efficiency when the each pile is basically behaving basically in an individual fashion. So that time you will be having somehow different group efficiency when it will be behaving in a block-wise fashion. Okay, so we'll see for the calculation of group capacity in pile in the subsequent problem. So how to calculate the load carrying capacity of a pile group in clay. So far we have basically determined the capacity of single pile using different formulas or different ways. Okay, so in the subsequent problems we will also see how to calculate the capacity of a pile group in clay. Okay. Okay. So to solve this problem, we'll basically use the formula which is given by Converse-Lavre formula. Okay, so to determine the pile group efficiency. So this formula this involves the number of rows of piles, and number of piles in a row, and a variable called theta. So if you know these three variables, so you can easily determine the group efficiency of the pile. Now for the given configuration of the group piles, what is the number of rows of piles? So number of rows of piles is basically 3. 1, 2, 3. And what is the number of piles in a row? So it's again 3. So as you can see, in each row there are 3 number of piles. Okay. And what is theta? It is the tan inverse of d by s, where d is the diameter of the pile and S is the center to center spacing. Okay, so you can define this theta in this fashion. Now what we will do, we will first use this equation to calculate the variable of theta by substituting the values of m, n and eta g, because m we know, n we know, and eta g also we know, because you have to figure out the center to center spacing of the piles for the group efficiency of 60%. Therefore eta g value you know, m and n, the configuration of the pile group is you know. Therefore you can easily determine the variable theta or this parameter theta by using this equation given by converse Laplace formula. Okay, so this eta g, it is 1 minus m times n minus 1 plus n times n minus 1 divided by n. Okay, so multiplied by now eta g, this is your 0.6 m 3 0.6 equals to 1 minus 3 minus 1 3 into 3 minus 1 divided by 3 into 3. So if you solve this equation, you will be ending up with the value of theta as 27. Okay, and this theta is defined as tan inverse d by s. So this is 27. So obviously this d by s, it will be tan 27, and s, this will be d upon tan 27. So this d value is your, what is the value of d for the given problem? So it's 300 mm. Okay, that means 0.3 meter. So therefore the center to center spacing for the pile group efficiency of 0.6, it would be 0.3 divided by tan 27. So 0.58. Okay. Okay. One more thing, which this is not basically within the scope of this problem. Still, for your kind information, that you should know what should be the minimum pile spacing in group of piles. Okay, so the pile spacing will basically, this group efficiency of a pile will be governed by this minimum pile spacing. When the spacing is too less or the spacing is too high, so depending on the value, you will be having different efficiency of the pile. Okay, so some minimum spacings are basically or is recommended for different type of piles. For example, end bearing piles, friction pile. Okay, so please go through that aspect. So to get an idea, what should be the minimum pile spacing for optimum group efficiency of the pile group, what should be the minimum pile spacing? So please go through that aspect. I hope this is given in the lecture materials released in the portal. Okay. Okay. Now we'll take problem 5. So this problem talks about the determination of said load carrying capacity of a pile group in plane. So a group of 9 piles with square cross section rest in a homogeneous clay of unconfined compressive strength 100 kPa. The length of the piles is 10 meter. The size of its cross section is 400 mm and by 400 mm, that is square. The piles are arranged in a square pattern and are spaced with a center to center distance of 1000 mm. Calculate the safe load carrying capacity of the pile group on the basis of shear failure criteria, considering a factor of safety of 2.5. So these are the few additional information given to this problem. The adhesion factor is 0.7. The bearing capacity factor contributed by cohesion is 9, and considered both frictional and in-bearing resistance. Okay. So as we were discussing in the previous problem, that when you will be determining the load carrying capacity of a pile group, you have to consider two scenarios. Okay, two scenarios you have to consider. So first of all, you have to consider the block shear failure. Okay, and secondly, single pile failure or individual pile failure. Now you have to consider these two scenarios and you have to calculate the corresponding load carrying capacity of the pile group, and you have to take the minimum of these two as the final ultimate load carrying capacity of the pile group. And obviously for calculating the safe load carrying capacity of the pile group, you have to divide that final value with the given factor of safety of 2.5. Now, what is this block shear failure? So for block shear failure, this pile group is basically failing as a block. So in that case, you will be having this ultimate load carrying capacity of the group as Cu NC, area of the group, plus cross sectional area of the group, plus Cu perimeter of the group times A. Okay, so this will give you the load carrying capacity, ultimate load carrying capacity, considering the block shear failure. Now what is the value of Cu? So Cu, so this is 100 by 2, that means 50 kPa. And NC, this will be 9, and this AG, the cross sectional area, so this will be B times B. Now what is the B? How to calculate the B? So you can calculate this B as 2s. So this is, you can calculate as 2s plus or 2 times 1000. So this is the center to center spacing between these piles, and as you can see, in one direction you are having two spacing. So 1000 multiplied by 2 plus half of this cross section of the pile, and in this side also half of this cross section of the pile. Okay, so this will be, if I write here, so this will be 1000, and this small part will be 400 by 2, and again this small part will be 200 by 2. So that means 2000. Okay, so all are in millimeter. So therefore this value would become 2 times 1000 plus 400. Okay, so this is basically in millimeter. So what we will do, we'll basically calculate this area in meter square. 2.4 square. So 5.76. So right now we are considering block shear failure. So therefore we are dealing with the overall area, cross section area of the block, and for calculating surface area it will be the whole perimeter, the perimeter of the block multiplied by length of the pipe. So that will give you the surface area of the block. Now one thing you can note in this equation, that when we have determined the ultimate load carrying capacity, or rather we can say the ultimate skin friction resistance of a single pile. So similar to the single pile case, so for the block shear failure it will be having two components. So the first one is for point bearing part, and the second one is for the skin friction part. Now for the point bearing part, it's okay. So it's basically similar to the previous case, that is for single pile case. So for single pile, here instead of AG, you have to consider the cross sectional area of individual pile. So this CU and C remain constant. However, this individual area of the single pile is replaced by the area, cross sectional area of the block. Okay. Now coming to the second component, so that is skin friction component. So earlier in the single pile case, we have considered one adhesion factor, but here no such adhesion factor is considered to calculate the skin friction part of the block shear, means block, the pile group. Why? Because when you will be calculating, we'll see, to calculate the ultimate load carrying capacity of the pile group considering single pile failure. So that time we'll see. So when the pile will basically fail in single as an individual, so each pile it will basically fail individually. So in that case, you have to consider this soil pile interaction. So this is the pile and this is the soil, adjacent soil. So you have to consider soil to pile interaction. So therefore you are encountering, or you are facing two different materials, so at the pile soil interface. So one is concrete and another one is soil. So therefore the adhesion factor will come into the picture. However, when you will be considering the block shear case, that is the group of the pile, or pile group is basically behaving as a block, and it's basically fail as if a block is basically failing. So in that case you will be having soil to soil interaction. Okay, so this is soil, this is soil, this is soil, this is soil. So for soil to soil interaction, since the material is similar at the interface, so this adhesion factor will automatically become 1. So there is no need to incorporate such adhesion factor to calculate the skin friction component in case of block shear failure. However, this factor will come into picture when the pile will fail individually, okay, instead of it's failing as a block. I hope you are getting my point. So now we have determined the gross area of the pile group. Now we'll calculate the perimeter of the pile group. So the perimeter of the pile group, so it's simply 4 times B. Now 4 times the B value is again 2.4 meter. So it will be 9.6 meter. Okay. Therefore, we can easily calculate the ultimate load carrying capacity of the pile group. So it will be 50 times 9 times 5.76. Okay, plus into the perimeter is 9.6 and the length of the pile is 10 meter. Perimeter of the pile group multiplied by the length of the pile will give you the surface area of the block. So please calculate. So if you calculate this value, it will be equal. It is 739 kilometers. Okay. So this is considering block shear failure. Now considering the case of single pile failure, so where the pile will behave individually, so in that case first we have to calculate the individual load carrying capacity of each pile, and it will be similar, as you know, because all the piles are having same geometry, same dimension, and it's basically embedded in a material, in a soil which is having the uniform properties or similar properties. Okay, the same soil, the piles are basically embedded. So therefore if you calculate the load carrying capacity of one individual pile, and if you multiply that load carrying capacity with the number of piles involved in the pile group, so that will give you the ultimate load carrying capacity of the pile group, considering the case or scenario where the piles are failing individually. Okay, so therefore this QUG, it will be n times QU. So here n, this is the number of piles in the pile group, and QU, this is the load carrying capacity of single pile. So therefore you can modify this equation further. So CU MC AP plus alpha CU. Now this time you have to consider the addition factor for calculating the skin friction resistance of individual pile. Okay. Now what is the number of piles involved in the pile group? So it's 9. CU, this is 50 kPa. NC, this is 9. Now what is the cross-sectional area of individual pile? So this is 400 mm times 400 mm. So it's a square cross section. So that means 0.4 square. Plus, what is the addition factor? The addition factor is given as 0.7 times 50 times AS. So AS means the surface area of individual pile, that is pi dl, not pi dl. So it will be pi dl for a square, for a circular pile. Since for this problem we are having square pile, so it will be 4bl. So 4b will give you the perimeter. Now if you multiply the length of the pile with the perimeter, that will give you the surface area of the pile. Now the dimension of each pile is 400 mm by 400 mm. So therefore it will be 4 times 0.4 multiplied by So if we calculate, then it will be 5, 6, 8, 8. Now we have to compare these two values. So considering block shear failure and considering single pile failure. So as you can see, the scenario 2 will giving us the minimum load carrying capacity. So therefore, to be on the conservative side, we have to consider this scenario 2. So QUG final, so it will be minimum of this 7392 and 56. Therefore, however, we have to report the safe load carrying capacity. So therefore, UG safe will be 5, 6, 8, 10 divided by the given factor of safety, which is 2.5 for the problem. It is 2275. So therefore, to determine the safe load carrying capacity of a pile group, you have to consider two criteria. So the first one is block shear failure and the second one is single pile failure. And you have to take the minimum of these two as the final ultimate load carrying capacity, and you have to divide that final ultimate load carrying capacity with the recommended factor of safety to get the safe load carrying capacity of the given pile. Okay. Okay, so this is for the determination of safe load carrying capacity of a pile group on the basis of shear failure criteria, considering a factor of safety of 2.5. Now, we'll take one example to determine the negative friction. Okay, so negative skin friction, it is also a very important aspect in pile foundation problem. So this example is taken from GATE examination 2018. So in this problem, a group of 9 piles in a 3x3 square pattern is embedded in a soil strata comprising dense sand underlying recently filled clay layer, okay, as shown in the figure. The perimeter of an individual pile is 126 centimeter. The size of the pile group is 240 centimeter by 240 centimeter. The recently filled clay has undrained shear strength of 15 kPa and unit weight of 16 kg per meter. The negative frictional load acting on the pile group is. So therefore, as you can see, this is the elevation view and this is the top view or plan view. Now from the elevation view, when the piles are basically embedded in a soil strata, it's having first a 2-meter recently filled plane, followed by a 5-meter thick dense sand. Now, in which layer, whether this recently filled clay, in the recently filled clay or the dense sand, you will be having this negative friction. That you have first figured out. Okay. So negative friction, you have to calculate, or you can calculate in a similar fashion as we have calculated the load carrying capacity of a pile group. So the methodology is similar to calculate the negative frictional load. However, there is a small difference. So that difference we'll see later on. So first we have to figure out in which layer this negative frictional load will be applicable. Okay, that means the length of pile for which this negative friction will be valid. Now, what is the load transfer mechanism? So when a single pile is basically loaded vertically and the pile is basically trying to compress the pile. Okay, so this load is basically trying to compress the pile. So this compression or this load will be resisted by shear stress mobilized along the length of the pile, which is known as skin friction resistance, and the point bearing resistance acting at the pile tip or pile base. So that's why when we try to determine the load bearing capacity of a or load carrying capacity of a pile, we calculate these components, two components individually, and we take the summation of these two to calculate the or to report the load carrying capacity of the concerned pile. So skin friction resistance and the point bearing resistance. However, one point is to be noted here, that in this mechanism we have considered that when this pile is subjected to some axial vertical load, the movement of the pile relative to the soil is basically downward, and it's obvious. So the relative movement of the pile or the movement of the pile relative to the adjacent soil mass is basically greater, and it's in the downward direction. That's why you are having the resistance in the upward direction, both for point bearing and for the skin friction. However, when you will be encountering some recently filled clay or unconsolidated clay, something like that, or loose sand, so what will happen? So in that case, the adjacent soil mass will basically settle compared to the or relative to the pile. So therefore, earlier in the problem where we are getting the frictional resistance in the upward direction, in this problem we are getting the frictional resistance in the downward direction, as if it is imparting some external load on the pile. So earlier the skin friction resistance acting in the upward direction, giving you the resistance against the externally applied vertical load. Here this skin friction is basically acting as if externally vertical load. It's an overburden over the externally applied vertical load. That's why this is called negative frictional load acting on the pile. So it's not basically contributing to the resistance, it's contributing to the load. Okay, so since this is negative in feature or negative in nature, and why it becomes negative, just now we have explained that for recently filled clay, when the pile groups are embedded or constructed and it's subjected to some externally vertical or applied load, the recently filled clay will try to settle, will try to consolidate, and as a consequence of that, the movement of this adjacent soil mass relative to the pile will be in the downward direction. So therefore the friction will be the skin friction along the length of the pile shaft or the pile will be acting in the downward direction. Okay, so if we draw the stresses, shear stresses, so this is the externally applied load on the top of the pile cap. So in at the it will be in the Again, in the dense sand, the skin friction will be in the upward direction. However, for the recently played clay, it will act in the downward direction. Okay. So therefore, it will not contribute to the resistance of the pile. So it will contribute towards the load. It's an additional load due to negative skin friction. Okay. Now, how to calculate this negative skin friction of the pile group? So this negative skin friction okay, someone is, I think, someone joined and no problem. Okay, to calculate the negative friction, you have to consider first both this block scenario and the individual scenario, that is this n fn and fng, and you have to take the minimum of these two. Okay, oh sorry, maximum of these two. So this is the difference, because earlier in the case we determined the resistance, so obviously to be on the conservative side we have taken the minimum of this individual and the block shear case. However, for negative skin friction, since this is a load, this is contributing towards the load, so therefore you have to consider the maximum of these two. Okay, so first we have to calculate the negative skin friction for individual pile, and you have to multiply that with the number of piles involved in the pile group. So this will give you one negative frictional load acting on the pile group, and then you have to calculate the negative friction load as if it's acting on the block, and then you have to take the maximum of this. Okay, we'll see how to calculate this two entities. So first of all, this Fn, so therefore we have determined, or we have figured out, in the recently filled clay portion will be only having the negative frictional load or negative skin friction. Okay, so Fn, so this will be alpha times C. So this is a simple formula for negative skin friction. Now what is the value of alpha? Okay, I hope it's not given to this problem, so you can take this value as 0.5. So somehow it's missed. Okay, so 0.5, and but okay, so this is the unit skin friction multiplied by the surface area of the pile, that will give you the ultimate skin friction. So 0.5 multiplied by 15 multiplied by AS. So what is the AS? What is the value of AS?
Area of, sir.
Surface area of the pile. So what is the length? So that for that you have to multiply the perimeter of individual pile with the length of pile. Now what is the perimeter of an individual pile? It's 126 centimeters. So therefore 1.26 meter. And what is the length of the pile? You should consider to calculate the negative friction.
What, sir? What, sir?
So AS, this is basically product of the perimeter of the pile and the length of the pile. Now perimeter of the pile, this is directly given to you as 126 centimeter. That means 1.26 meter. Now I am asking about the length of the pile. To calculate the length of the pile, what value we should take? So should we take the
Sir,
huh?
यस 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 वैल्यू सर निकाल के इसको हम निकाल सकते हैं ना लेंथ सर,
How?
जो सेंटर टू सेंटर डिस्टेंस रहता है सर, जो डायामीटर ऑफ पाइल का जो रहता है सेंटर टू सेंटर डिस्टेंस सर।
No. I am talking about, so this is suppose your one individual pile. Okay. So this is your perimeter. This distance will give you the perimeter. So for a circular pile, suppose
तो
this is pi d,
सर
and pi d is
तो
given.
सर सर तो ये जो पाई डी इंटू यल का जो फॉर्मूला रहता है ना सर पेरीमीटर का सर, सरफेस एरिया का,
हाँ.
तो सर हमें पाई का वैल्यू भी दिया हुआ है, डायामीटर भी दिया हुआ है, तो सर हम अब पेरीमीटर दिया हुआ है तो ये उससे यल नहीं निकाल सकते सर?
No, this is perimeter. This is not the surface area. Surface area is basically perimeter into length. So how you can determine the length from perimeter? So perimeter and length are two different entities. So you have to calculate the AS, the surface area of the pile. So for that you need to know these entities separately, perimeter and length. So perimeter is given as 126 centimeter. But I am asking about the length. How you should calculate this length, or what value you should consider for this length. So length, I hope it's clearly visible from the slide. Now, what is the total length of the pile? So the total length of the pile, this is 2 meter plus 5 meter. This is 2 meter, this is 5 meter. The piles are embedded in a soil strata comprising dense and underlying recently filled clay layer as shown in the figure. So 2 meter, this is for the recently filled clay portion, and dense sand, this is 5 meter. So 2 plus 5. So this will give you the total length of the pile. But I am asking that what value we should take. Should we take this 7 meter as a whole to calculate the negative frictional load on the pile?
यस सर।
No. No, we should not take, because we have just now explained. So this negative skin friction will only be valid for the upper recently filled clay portion. So for this layer, we'll be having the negative skin friction, not for the dense
और तो
sand.
5 मीटर सर।
So it will be 2 meter. The thickness of the recently filled clay
सर
is 2 meter.
बट अपोजिट रिएक्शन इज द 5 मीटर ना सर, नेगेटिव फ्रिक्शन।
No, negative in the recently filled clay, na? As you can see from this. So this is the negative skin friction. So when friction are acting basically in the upward direction, it's considered to be positive because it's contributing to the resistance. So this is the externally applied vertical load on the pile top. So for that, you will be having mobilized friction resistance and mobilized point bearing resistance. So that will give you the resistance of the pile. But for the negative skin friction, when it will act in the downward direction, it will not give you the resistance of the pile. It will behave as if an additional load acting on the pile. So it's negative in that manner. Okay. So therefore, you have to basically
यस सर।
consider the length of the pile which is involved in the recently filled clay, since negative skin friction is observed only in the recently filled clay layer. So therefore this value would be 2. So 0.5 times 15 into 1.26 into 2. So this will give you 18.9 kilonewton, and this is for single individual pile. So this much negative frictional load will basically act on a single pile. So therefore, to get the negative frictional load acting on the pile group, you should multiply this value with n. Okay. So n times Fn, this will be 9 times 18.9. 9 times 18.9, how much? 170.1. So this is considering the single pile case. Okay. So we first we have first determined the negative frictional load acting on a single pile, and we have multiplied the number of piles with that load to calculate the frictional load, negative frictional load acting on the pile group. Okay. However, to calculate the negative frictional load for the block shear case, for the block scenario, so it will be Cu into As plus, or here you can write Cu EGLC plus gamma Hg. Okay. Now earlier in this case, you have basically considered this is the friction which is basically acting. So suppose this is the pile, so this is the load, and you are having the negative skin friction in this fashion. So therefore it's alpha Cu As, adhesion factor you should consider. Okay. Now considering the this group case, so you will be having soil to soil interaction, so therefore there should not be any alpha. And one more thing, this soil, the weight of this recently filled clay, that also you should consider. Okay. So this Cu, this is 15, then this perimeter of the whole pile group, this is 4 times 2 4 multiplied by LC. So again this is 2 meter, so this is your LC plus this is the weight of the recently filled clay, because that will also give you the overburden in the downward direction. Okay. So the unit weight of the soil is, I hope, given as 16 kilonewton per meter cube. So this is 16. And what is the area of the pile group? So this will be 2.4 times 2.4. That means 2.4 square, and LC is 2 meter. Okay. So therefore it would be 15 times 4 times 2.4 into 2 plus 16 into 2.4 square into, so 472. So considering the block case, you are having the negative frictional load acting on the pile as 472.32 kilonewton, and for the single pile case you are having the negative frictional load acting on the pile group as 170.1 kilonewton. Okay. So this is considering n times Fn. So first you are calculating the negative friction load acting on individual pile, then you are multiplying the number of piles involved in the pile group. So in that fashion you are getting the negative frictional load on the pile group as 170.1 kilonewton, and considering the block case you are having the negative friction load as 472.32. Now since this is the driving force, this is not resistant, so to be on the conservative side, so the final value would be maximum of this 171 and 472.32, that is 472.32. This will be the answer. So this is opposite to the previous problem. Okay, so this is basically so in the previous problem, when we determined the load carrying capacity of a pile group, we considered the minimum of these two values, 7392 and 5688. So 7392 we have got from this considering block shear failure, and 5688 we have got considering single pile failure. So to be on the conservative side, we have considered the minimum of these two values, which is 5688 kilonewton. However, for this problem where we have to report the negative frictional load acting on the pile group, we have to consider the maximum of these two values. Okay, so which is 472.32 kilonewton. Okay, so this is the last problem for this session, and this problem is basically interlinked to one problem in the previous session. Okay, so a square driven pile group of 9 piles rests on a sand stratum. The center to center spacing of piles is 1.2 meter and the diameter of a single pile is 0.3 meter. The load settlement data of a single pile is given below. What would be the settlement of the pile group if each pile in the pile group is subjected to the same average load allowable for a single pile as per IS 2911 part 4 1979, and you have to use Kempton's method. Okay, so earlier in the previous session we took one problem where we have basically determined the allowable load for a single pile considering the load settlement data obtained from performing the vertical load test on that pile. Okay, so this is the load settlement data. So in the first column you are having the load, and in the second column you are having the settlement. Now what does it recommend? This Indian standard IS 2911 part 4 recommend. So it recommends that the allowable load on a single pile shall be lesser of the following. So for the first case, it will be 2/3 of final load at which the total settlement attains a value of 12 mm. And in the second case, it will be the 50% of final load at which the total settlement equals to 10% of the pile diameter in case of uniform diameter piles, and 7.5% of bulk diameter in case of underend piles. So since this is the uniform diameter pile, so you have to consider 10% of the pile diameter. And I hope we already solved this problem and we have determined the allowable load for a single pile. Okay, so this is the load settlement plot utilizing the data. Now first of all, we have determined the Q allowable considering the first condition as 2/3 of load at which the settlement is 12 mm. So corresponding to 12 mm settlement, we have determined the load from this load settlement plot as 750 kilonewton. So this is the final load corresponding to 12 mm settlement. So 2/3 of this final settlement will give you an allowable load of 500 kilonewton. Now coming to the second condition, so you have to first calculate the 10% of the pile diameter. Now pile diameter is 0.3 mm. So 10% of this 0.3 meter will give you 30 mm settlement. Okay, so corresponding to this 30 mm settlement, you will be having the load from this plot as 1700 kilonewton. So 50 times 50% of this final load will give you an allowable load of 850 kilonewton. Now minimum or lesser of these two values will give you the final allowable load for a single pile case, so which is 500 kilonewton. Already we had solved in the previous session. Now in this session, through this problem, we'll see how to extrapolate the settlement of an individual pile to the settlement of a group of piles. Okay, now one condition for that we need to satisfy, that each pile in the pile group should be subjected to the same average load. Okay, so if this is the scenario, then we can extrapolate the settlement of an individual pile to the settlement of the group pile. Okay, how that we'll see, and for that we'll use the Kempton's method. Now first of all, we'll determine the settlement corresponding to this allowable load 500 kilonewton. Why? Because it's mentioned that each pile in the pile group is subjected to the same average load allowable for a single pile as per IS 2911. Therefore, the settlement of an individual pile is not directly given to this problem. So first of all, we have to calculate the allowable load for a single pile case. Then we have to calculate the settlement corresponding to that allowable load. Now, for the given problem or for the given load settlement data, we are getting the allowable load for a single pile as 500 kilonewton, considering this IS recommendations. So corresponding to this 500 kilonewton, we'll have the settlement as 8.5 mm. So the individual pile settlement is 8.5 mm. So this corresponds to an allowable load of 500 kilonewton. Okay. So again, we can determine this individual pile settlement from this load settlement plot. So this is the 500 settlement. This is the 500 load. So corresponding to this 500 kilonewton load, you can determine the settlement. Okay, so it's 8.5 mm. Now, how we can extrapolate the settlement to the settlement of the pile group? So we can extrapolate in this fashion. So this method is basically recommended by Skempton. So here the group settlement divided by the individual pile settlement is expressed in this fashion. So 4b plus 2.7 divided by b plus 3.6. And please keep in mind, this method you can apply when for same average load, means same average load is basically acting in all the piles involved in the pile group. So only in that case the settlement ratio of group of pile with a single pile can be obtained in this fashion. Okay. Now what is B? So here B, this is nothing but the dimension of the pile group. So this is B. So to calculate B, it will be 2 times the center to center distance between the piles. So which is given as center to center spacing of piles 1.2 meter plus the diameter of the pile, which is 0.3 meter. Okay, so that will give you the value of B. So 2 times 1.2 plus 0.3, that means 2.7 meter. So therefore this ratio Sg by Si, it would be 4 times 2.7 plus 2.7 divided by 2.7 plus 3.6 whole square. Now if you simplify this equation, so you will be getting this group pile settlement as, so first of all you have to calculate this ratio. Okay, so 4 times 2.7 plus 2.7 divided by 2.7 plus 3.6 whole square. So this ratio multiplied by the individual pile settlement, which is 8.5 mm, already we have calculated. So this will give you the group pile settlement as 39 mm. Okay, approximately 39 mm. So using Skempton's method, we can extrapolate the pile, the individual settlement of an individual pile to the settlement of a group pile. Now this is for Skempton, the methods which is given by Skempton. Now again you can, I hope, use the method which is given by Meyer. So following this methodology also, you can determine the group pile settlement by using this equation. So this is the ratio group pile settlement to the individual pile settlement, but the equation is the ratio is different. So earlier the ratio is basically dependent on the dimension on the group pile, but here this ratio is dependent on the ratio of pile spacing to pile diameter, which is S, and the number of rows in the pile group. So these two parameters you should know before calculating this ratio of group pile to the individual pile settlement. Okay, so this is a homework for you. So please.
So how to find the yes, sir, in this question formula, sir?
Which one?
In this formula given yes, no, sir. Ratio of pile spacing to pile diameter. That yes, how to find, sir?
So what is the pile spacing for this problem?
1.2 meters, sir.
And what is the pile diameter for this problem?
0.3, sir.
So 1.2 divided by 0.3, that will give you the value of S, na?
Oh, okay, sir. Thank you, sir.
Okay. Okay. So
Yes,
please,
sir.
please solve this problem. Okay. Now we'll end this session by taking one more problem. So this is in relation to problem 5. So for the pile group given in problem 5, calculate the total corrected settlement using the additional information given below. So water table is at the ground level. The saturated unit weight 20 kN per meter cube. Compression index 0.15, initial void ratio 0.7, elasticity modulus 3 times 10 to the power 4 kilonewton per meter square, Poisson's ratio 0.4, influence factor 1.12, rigidity correction factor 0.8, depth correction factor 0.58, pore pressure correction factor 0.7, and assume the load dispersion rate to be 2 vertical is to 1 horizontal. Okay, so all the necessary information you should require for solving this problem are directly given to you. Just you have to calculate the total corrected settlement. Okay, now the settlement calculation, just in the earlier problem we have seen through the use of this Kempton's method and Mayer's method, for which we need to know the load settlement plot or load settlement data for a single pile or the settlement of an individual pile. So that was the information we should know to follow the method outlined by Mayera or Kempton. So in this problem, so this is basically similar to the earlier shallow foundation problem. Okay, so just you have to note a few things very carefully, that this total settlement, this is the summation of immediate settlement and the consolidation settlement. Okay, secondly, what are the corrections we should incorporate? So as you can see from this problem, that one is rigidity, then depth, and pore pressure. Okay, now this rigidity and depth correction applies to both the components. Okay, so it's applicable, or these corrections, these two corrections, rigidity and depth corrections, are applicable to both these components, that is immediate and SC. However, this pore pressure correction, this is only applicable for the which component, immediate or consolidation?
Consolidation, sir.
Yeah, very good. So this is only applicable for the consolidation settlement. So first we will calculate the immediate settlement, and obviously this is uncorrected, by using this formula. So Q n times B 1 minus mu square IF by E. Okay, then we'll multiply with the rigidity correction factor and the depth correction. Okay, so this will give you the SI correction. And for consolidation, so this will be CC divided by 1 plus C0 times log of sigma 0 prime plus delta sigma divided by delta sigma, sigma 0 prime. So this will give you the first uncorrected consolidation supplement. Then you have to multiply with 3 different correction factors. So rigidity correction factor multiplied by depth correction factor and pore pressure correction factor. Okay. And finally, the ST total corrected. So it will be SI corrected plus SC corrected. So this will give you the corrected total settlement for the given pile group. Now, these parameters we should know, okay, before calculating this individual component, means immediate and consolidation. So what is the value of Qn? So Qn, this is the net load intensity which is basically acting at a depth of 2 by 3L from the pile top. Okay, so there are several conditions talked about in the lecture videos. So depending on that, this distribution, this depth, you should basically figure out. So at which level or from which level this distribution of space will basically start. Okay, so since this is homogeneous clay, so the distribution will start at a depth of 2/3 by length of the pile from the pile top. So if this is not the case, suppose this is not homogeneous clay, this is a layered strata, and for the upper layer it's a weak clay and followed by it's a strong clay, then this scenario will not be valid. So the distribution or dispersion of stress will basically start. Okay, so I am talking about this scenario. Suppose this is the weak layer and this is the strong layer and this is the pile length total. Okay, so in that case this weak layer will basically settle with this pile group. Okay, so your distribution, suppose this length is L prime, so somewhere here the distribution will start. L prime. Oh, sorry, this is not L, this value is here. And again, if the soil is completely weak, means up to the pile tip, so this is the pile length, so this portion is weak, means along the entire length of the pile, then you are getting some rigid or dense stratum, then the distribution will start from the pile tip only. So depending on the scenario, so this is very crucial point to determine the settlement of a pile group. So at from which or what level the distribution or dispersion of stress you should consider. Okay, so this intensity of loading or this intensity of stress, this is Qn. So Qn, this you can calculate from the safe working load, that is Q safe, divided by the area of the pile group, so that is B times L. Okay, so we will not use this L for dimension, so suppose this is B times L. Sorry, B times B. That is the so suppose this is the pile group cross section, 9 pile. Okay, so this is B and this is B, and this pile group is subjected to safe working load. Now this safe load, this already we have worked out. Okay, so in problem 5 we have worked out the safe load carrying capacity of the group of pile as 2275 kN. So we will basically consider this load for the calculation of Q1. 2275 divided by, now what is the dimension? The dimension, it is, I hope, 2.4 meter. Yeah, so it was 2 multiplied by 1000 plus 400, 2.4 meter. So 2.4, this much kilometer. So B is your 2.4. Okay, now first we'll talk about the immediate part. So Qn B, we know the mu value, so this is given as 0.4. Then IF, this is, I hope, given as 1.2, which is the influence factor. Then elasticity modulus. Okay, so E value 3 into 4. So if we substitute these values in this equation, we can easily calculate the uncorrected immediate settlement. And if we multiply this uncorrected immediate settlement with the rigidity factor, which is 0.8, and the depth correction factor, which is 0.58, we will get the corrected immediate settlement. Okay. Now coming to the consolidation part, you should know this data. CC, so CC compression index, so this is given as 0.15, then 0.15. Then you should know the initial void ratio of the soil, which is given as 0.7. Then you should know the thickness of the stratum. Okay, so thickness of the stratum will take the influence zone width as 2 times V. Okay, so the same thing we have considered for the calculation of consolidation settlement of shallow foundation. So for that, in that case also we considered it as 2 times V. V is the dimension of the group part. So this will be 2B. That means 4.8 meter. Okay. Now another 2 parameters we should also know, that is the initial effective overburden pressure at the center of this 2B stratum and the delta sigma prime. So this sigma 0 prime we can easily calculate because we know that the unit weight, saturated unit weight of the soil, we know the unit weight of the water, we can take it as 10 kN per meter cube. So therefore we can easily calculate the submerged unit weight of the soil, which will be 20 minus 10, that is 10 kN per meter cube. Now if we multiply, so sigma 0 prime, so at this level, suppose this is A, so sigma 0 prime, so at A, so this will be simply 2/3 L plus B times gamma psi. So we know L, so the length of the pile is, I hope it was 10 meter. Okay, so please check it from the problem 5, and B 2.4. gammas are 10 kilonewton per meter cube. So we can easily determine the sigma 0 prime. Now coming to delta sigma, so that is the additional stress increase at the center line of this 2B, considering a load dispersion angle of 2 vertical is to 1 horizontal. So you can calculate this additional stress increase as Qn B times B square. So that is the net load at this level, okay, divided by this dispersed area. Now what is the dispersed area? So it will be B plus B. Okay, so you are calculating the stress increase at a depth of B from this start of dispersion. Okay, so therefore to go a depth of B with an angle, this 2 vertical is to 1 horizontal, the added dispersion, this will be B by 2 and this will be B by 2, and this was already B. So B plus B by 2 plus B by 2, that means B plus B 2B times 2B. Okay, so this will give you the additional stress increase at this level A. So Qn you know, B you know, so you can easily determine the delta sigma. Now once you determine the uncorrected consolidation supplement by using this formula, then you have to multiply this uncorrected supplement with the rigidity correction factor, depth correction factor and the pore pressure correction factor, and you will get the corrected consolidation supplement. Now after getting the corrected consolidation supplement and the corrected immediate supplement both, you have to just add these two components to get the corrected total supplement. Okay, so I will not be able to solve this problem in details anymore, so I am giving you the final answer. So I hope you will get this total corrected supplement as 58 millimeter. Okay, so please solve this problem and cross check whether this value is correct or not. Okay, and let me know about any difficulties which you face in solving this problem in the next session. So this is for today's session. So we'll again meet on next Sunday on 24th September at 5 p.m. and thank you for joining this session.
So, sir, can you please show me from the first presentation?
Please wait for a few minutes. Okay.
Okay, sir.